Hi folks, Mr. Long here. I'm going to do a screencast today to introduce you to the derivatives of exponential and logarithmic functions. Specifically, we're going to develop a special function called the Euler function or Euler function, which is a really neat function. So the first thing I want you to think about here is what does the derivative of an exponential function look like? So, for example, if I draw a simple exponential function like, oh, I don't know, 2 to the x, something like that, it'll look like this, right? Just grows without boundary. So there's y, there's x. So then if I draw tangents, so I can have a tangent there, a tangent there, a tangent there. And I notice that, what do I notice? The tangent slope here is quite steep. The tangent slope here is less steep, so maybe it's down here, and the tangent slope here is quite flat. Well, look at that. So what would you say is true about an exponential function in terms of its derivative? What do they look like? Well, they look pretty similar. They look pretty similar. So if we go over to here, what we've got is an exponential function right here. Right, and I'll just draw that nice curve. And we've got a couple of tangents. And the tangents are right there and right there. So if we were to look at this one, I've actually got some slopes on here. So if these are tangent equations, what is this? What is the slope of this line? 0.693. So, and that's at the point of tangency of x equals 0. So 0.693 would be, if that's 1, 0.693 is maybe right there. And I should be doing this with a different color. It's maybe right there. And then over up here, we know that this tangent equations are f prime at a, x minus a, plus f at a. So a is equal to 1. Okay, so this is what the tangent slope is at x equals 1. And the slope is 1.386. Well, this is 1, this is 2, 1.386 is right about here. Well, look at this. If I do this, so there's my tangent slope function. What do you know? Take a look at that. So what's true about the tangent slope function and the original function? Well, they look almost the same. They almost look parallel. They have that same, they go from very low steep to, or not very steep to very, very steep. So it looks quite interesting. Okay, so I noticed that they are shaped very similarly. By the way, yeah, what information can you take from the tangent equations? Well, from the tangent equations, you can take that, in this case, f prime at a is 1.386. You know that a equals 1, and you know that f at a is 2. So you know that the ordered pair the tangent is taken at is 1, 2, which makes perfect sense because that ordered pair is 1, 2. Okay, 1, 2. So I've got these tangent equations and I can get all kinds of information. And we're going to need that as we move through the investigation. So let's do the investigation now. Okay, so what we're going to do is go through a variety of functions and examine the tangent equations to see what information we can take. So we've got 2 tangent equations and I'll circle those. So the first tangent equation is that one there. And the second tangent equation is that one there. I'm going to look at the second tangent equation first because it's actually easier to look at. So 1.386 x minus 1 plus 2. So that tells me that the x value, the a value, is 1. The f at a value is 2. So in other words, if x is 1, the y value is 2, and this tangent slope is right there, 1.386. 1.3, whoops, it's an 86. All right, what about this tangent? Where is that tangent located at? That tangent is located at x equals 0. Okay, x equals 0. So because it's actually, I could write that as 0.693 times by x minus 0 plus 1, right? X minus 0, if it's just x by itself. So that means the y value is 1. This is 0.693. Okay, so what I'm going to do now is to take y prime and divide by y. Well, this is pretty easy to do for the first one because I can just do 0.693 divided by 1, which is 0.693. Here I can go 1.386 and divide that by 2 and use my calculator, 0.693. Interesting, it's a constant. So if I take the slope and I divide by the y value for y equals 2 to the x, I get a constant. That's interesting. So what does y prime over y always equal for 2 to the x, for y equals 2 to the x? Well, it always equals 0.693. Now, if I multiply both sides by y, I will get y prime equals 0.693 times by y. But what is y worth? What is y worth? What's the value of y? I think we know. Y is equal to 2 to the x. So I can replace that y with 2 to the x. Okay, so it's y prime is equal to 0.693 times by 2 to the x. Okay, I'll put that in a bracket just to show that that's 2 to the x. So that's the derivative or the tangent slope function for 2 to the x. So what is that really? It's 2 to the x multiplied by 0.693. We call that a vertical scaling, right? Or we could call it a vertical compression. Okay, what I'd like you to do right now is to pause this video, and hopefully you've got a copy of this. Either you've printed out a copy or you have a digital copy, and I'd like you to fill in the same thing for this table. So please pause, take the time to do it, okay? It really is worthwhile for you to do it because it requires you to do some thinking. Otherwise, you're just copying. So just pause the video right now and fill in this table. Okay, we're back. So hopefully you paused it, filled in the table, and it might look something like this. It might look like, oh, I don't know, the y value would be 1, right, from that one. And then y prime would be 1.386. And then if I divide those two, y prime divided by y is going to be 1.386. Then I move to the other tangent. And the other tangent is at x equals 1 and y equals 4. So 1 and 4. And y prime is 5.545. So the slope is 5.545 when x equals 1 and y equals 4. And if I divide 5.545 by 4, I get 1.386 again. So again, I've got a constant. Every time I take y prime, the derivative, and I divide by y, I get 1.386. Or in other words, well, we're going to see here what it means. So y prime over y is 1.386. I'm now going to multiply both sides by y, and I'm going to get 1.386 multiplied by y. But what's y worth? Well, y is worth 4 to the x. So 1.386, but this y right here, folks, is worth 4 to the exponent of x. And so that's what y prime is worth for this. So I want you to notice up here, if you have 2 to the x, the derivative is 0.693 times 2 to the x. For 4 to the x, it's 1.386. So what does that tell us? That somewhere in between 2 to the x and 4 to the x, what will be true? So the derivative of 2 to the x is just about, well, it's 69% of 2 to the x, right? So it's in other words, it's about 31% less than 2 to the x. This one is 38.6% more than 4 to the x, right? So the derivative here is 31% less than 2 to the x. Here it's 38, 39% more. So in between 2 to the x and 4 to the x, what's going to happen? That there's got to be a number somewhere where this number is 1. So it's 100% of the original function. And what would that mean? If the derivative was 100% of the original function, what would it be equal to? Well, let's see. So I've done the hard work here, and well, not really. I knew this. So if I go 2.718 to the x, which is in between those two, you're going to notice something. Look at this. So remember that this is f prime at a, and this is f at a. By the way, that's x equals 1. So when x equals 0, f prime at a is 1, f prime at a is 1, and f at a is 1. So in between those two is this. I get a y value of 1 and a y prime value of 1. I get a y value of 2.718 when x equals 1, but I get a y prime value of 2.718. If I divide these two, y prime by y, I get 1. So y prime over y is 1. Multiply both sides by y. And I get 1 times y. But what's y worth? Y is worth 2.718 to the x. So I don't need to show multiplication by this 1. I just don't. But what I need to do is I can write this as 2.718 to the x because that's what y is worth. So look at this now. If y equals 2.718 to the x, what does y prime equal? The exact same thing. So the tangent function and the original function are the same. This tells us some interesting information. So if bacteria was growing according to this, which by the way is growth by 2.7, so 1 to the x is keeping 100%. So 2.7 is growing by 170%. So if bacteria was growing this way, if I had 100 bacteria, the bacteria would be growing by 100 bacteria per minute. Okay? So it's a special number where the derivative and the original function overlap. The slope, tangent slope, is the same as the y value. This is Leonard Euler or Euler. He is a German mathematician who discovered this, amongst many other things. And we call this number e, and it's a number just like pi. So 2.718 ... It goes on forever. Okay, it's an irrational number that doesn't have terminating decimals. And it's very special because the y value of the original function equals the tangent slope. They're the exact same thing. Okay. So what does that mean then? Well, let's go up here and do some examples. So if I have e to the x, remember that e is just a number, 2.718 ... that goes on forever. The decimals don't terminate into any sort of pattern. So if I have the function e to the x, the derivative of that is just e to the x. Okay, e to the x. The derivative of e to the x is e to the x. Really, really useful pattern. Result. Okay, so now we're going to do some examples of derivatives of e to the x. And so what we've got here is we want to do the derivative of 5 e to the sine x plus 1. So first thing I would do is simplify this. I'm going to take the 5 outside here, and I know that, excuse me, the derivative of a sum, so there's two values inside there, is the sum of the derivatives. So I'm going to take the 5 outside, and then I'm going to write e to the sine x here, plus the 1 separately. And that's a nice way to rewrite this, okay? In fact, that's the way it should be rewritten. I know that you're probably not going to take the time to do that when you're doing your homework, But on a test, that's a very good thing to show because it demonstrates to the person marking that you understand the best way to simplify a derivative before you actually take the derivative. Because remember, d by dx means you haven't done it yet. So what's the derivative of that? Well, that's 0. Then that leaves us with this to differentiate, right? And then multiply by 5. So is that a composite function? So is there a function inside a function? Well, normally you would have e to the x, but instead of e to the x, you have e to the sine x. Okay, so it looks like we've replaced x with sine x. So that's a composition of functions. We have a function inside a function. So in this case, if you notice, we've got, I'll write it over here too, f of g of x. We're going to write this a little bit differently now, instead of using u. This is the inside, right? G is the inside, f is the outside. Okay, so f is the outside, g is the inside. So what's our inside function? Well, it's sine x, right? Our inside function is sine x, and that's g. So g is sine x. So instead of u, because it matches, then it starts to match function notation form. Okay, function notation form. So we are going to use, when we use Leibniz, this is Leibniz, dg by dx, and then function notation, it matches now. So the first derivative I do is dg, g's on this side, x is on this side. Well, that's cos x. Well, what's the outside function? The outside function is f, and that's e then. E, and what is the inside function? Well, it's right here, right? It's right there. So e to the, I would put a g here, right? That's the inside function. E to the g. I would have put e to the u before. So what's that derivative? Well, the derivative of e to the g is just e to the inside function g. Okay, so when you're laying this out, it's always going to be this way, okay? This right here is your g. So we've got that. So now I just need to multiply these two derivatives, and y prime is going to be cos of x multiplied by e to the g. But what is g worth? G is worth sine x. Okay, folks, there's your derivative. That's y prime with the chain rule. Oh, and of course, there's a 5 there, which I almost forgot again, like I always do. Okay, so 5 cos x, excuse me, e to the sine x. Now we're going to do an example with the quotient rule. So for this one, again, I would take the 4 out front, and I would then have x squared over e to the 3x. Now, just off to the side here, I'm going to do some derivatives. D by dx of e to the x equals e to the x. D by dx e to the 2x. Well, what's the inside derivative? We can do the chain rule here without doing it. What's the inside derivative of that? 2. So it's 2 multiplied by e to the 2x. D by dx of e to the negative 5x. Well, what would that be? Well, the inside derivative is, looks like a 3. So the inside derivative of 5x, negative 5x, is negative 5. So this would be negative 5. Then I write the original equation, e to the negative 5x. Okay, so when we have a number inside here, we just multiply by that. If we have a variable that's not x in there, we just multiply by the derivative of the inside. Okay, so I go to this one here. So the top is there, it's x squared. Top prime is 2x. The bottom is e to the 3x. The bottom prime would be 3e to the 3x. And then I have to do my, and I didn't write it the same way as I normally do, but top prime bottom. That's the first one I do. And then I do, the second thing I do is this one, but it's a negative. Okay, so I change that sign to a negative because I'm subtracting. So it's going to be 2x times by e to the 3x, which is going to be 2x e to the 3x. Then it's minus x squared times 3e to the 3x. So I've got a negative and a 3. So it's going to be negative 3x squared e to the 3x. Negative 3x squared e to the 3x. And that's going to be divided by e to the 3x squared. Okay, now I need to simplify this. How do I go about simplifying this? Well, I have to do my common factoring. So I've got x as a common factor because I've got x and x squared. And I've also got e to the 3x and e to the 3x. So I'm going to factor out x, e to the 3x, and then I divide, right? That's how I do common factoring. So I do 2 divided by, that's a 1 there. So then I have x divided by x, that's gone. E to the 3x divided by e to the 3x, that's gone. So all I'm left with is 2. Okay, all I'm left is 2. And then I've got 2 minus 3. And then I've got x squared divided by x, which is going to be x. And that's it. 2 minus 3x, right? Because e to the 3x is factored out. Now we can do some simplifying. So I have e to the 3x divided by e to the 3x squared. E to the 3x divided by e to the 3x squared. If I had, just off to the side I'll do this. If I had a divided by a squared, that would equal 1 over a. So if I have e to the 3x divided by e to the 3x squared, that's 1 over e to the 3x. Okay, so what I can do then is cancel that out and cancel one of those out to have only one factor left. So my final answer is going to be x multiplied by 2 minus 3x over e to the 3x. Okay, e to the 3x. So, and that's y prime. All right, folks, so hopefully you understand that. So what we did there is we developed the idea of Euler's function, where the derivative of the original function is the exact same as the tangent slope. And we practiced the chain rule and the quotient rule and did some algebraic simplifying. Okay, so what you want to do now is do the part A questions. Okay, some of the part A questions in the overview, in the page that describes all the work that you have to do for this unit. Okay, have a good day.